Okay, we showed that the probability of event 1 goes to 0. That means the sequence emitted by the source is not jointly typical, xn and yn. We already showed that the event 2, that the encoder 2 doesn't find a sequence xn of w(v1) that is equal to xn of the first sequence which is emitted by the source. We estimate this already. The same estimation works for yn, so for encoder 2. It's exactly the same. Let's look what we have. 1 we showed already, that's just the theorem we had. For 2 we showed that R1 plus R1 prime must be bigger than the entropy of X times 1 plus epsilon. And for 3, we have the same, just that the R2 plus R2 prime have to be bigger than the entropy of Y times 1 plus epsilon. Now we have to look at the event that everything goes fine for the encoder and for the decoder. Both find a sequence, both send a W to the decoder, but then the decoder chooses the wrong V1, V2, and so an error occurred. So let's look at now this event 4, that's the event 4, and we consider it together with an AND with the complement of E1, E2, and E3. So we can write this because event E1 means that we just consider jointly typical sequences emitted by the source. We assume that the sequences emitted by the source are jointly typical, so we can sum over all jointly typical sequences and look at these probabilities under the condition that xn, yn, the random variables are equal to xn, yn. Of course, now we considered for E4 only single events. For each V1 and V2, we consider the event that the wrong code word was chosen. So therefore, we can write this in this way. Now we have to think about, so we know that V1, V2, W1, and W2 are functions of the source variables xn and yn in the code books, and the source and code variables are statistical independent. That's because how we construct the code book. Of course, therefore we can remove this condition here again in 78. So after we set xn w1 v1 equal xn and yn w1 v2 equal yn. So we can write these probabilities in this way. And remember, we want to have this part here small. Now we look at this, and we look at the probability of v1, v2 times that v tilde 1 is unequal v1 under this condition, and the sum that v tilde 2 is unequal v2 under this condition, and the sum over all v tilde 1 is unequal v1 and v tilde 2 is unequal to v2. So both things are true. If you look now at the terms, then we know that the probability that this part here is jointly typical is always, like we proved in the theorem, 2 to the minus n times the mutual information of x and y, minus 3 epsilon times the entropy of x and y. And of course, how many sequences are there? There are exactly 2 to the n r1 prime plus r2 prime here. So in totally, to get this small here, we have to choose that R1 plus R2 is smaller than the mutual information between X and Y minus 3 times epsilon and the entropy of X and Y. Okay, what do we get? I will show you on the board after this slide that this 3 equations we get, that the probabilities are small, implies that R1 must be bigger than the entropy of X, conditional on Y. R2 must be bigger than the entropy of Y, conditional on X. And R1 plus R2 must be bigger than H of XY. This rate we can assume with this coding method. And we get this rate region. These are all rates which fulfill this equation here. So, and we remark again that separate encoding of the source, the point R1, R2 equals HX, HY. So that means first the encoder 1 do the compression, then the decoder 2 do the compression. That would be HX and HY. Only if they work together, if it's just one encoder, we know that we can approach that H of XY. But you see, you can also, Slepian-Wolf, give a coding strategy that we can also assume this also if the two encoders do not work together. Now I will show you that this really follows from our three equations.